Let's do another example of reversing the order of integration. For this example, we have a region that has a boundary curve that's a trig function. So when we've got the trig functions, we usually have to work a little bit harder. But when we look at this, we see that the independent variable x is bounded below by negative pi over 2 and above by pi over 2. And of course, y runs from 0 to cosine x, the dependent variable. And this is an example from the lecture notes. And I wanted to add a little bit more detail to it because often we can look at a picture and think, oh, well, that obviously must be the answer. Well, that's not always the case. And when you're doing calculations, it's good to know that they're actually valid. So first, I want to make a very simple observation. We can see here that when x is 0, the largest the cosine will be is 1 clearly. So y will run from 0 to 1, and that's an observation that I've put here in this box, which is the simplest part of the problem. Usually determining what happens to the independent variable in the new order is usually quite simple. Now what we want to do is look at the x variable and see what happens to it, because now it's going to be dependent. Now before we do that, I just have written a little bit of information about the inverse cosine function. From your trigonometry and pre-cal, what you do is you restrict the domain of the cosine function to make it 1-to-1. And of course, the inverse cosine function has a universal definition. So what we have is a domain from -1 to 1 and a range from 0 to pi. And of course, in Cal 2, you prove actually that this is a decreasing function. So one thing that's nice about this, of course, the derivative is just the additive inverse of the derivative of the inverse sine, another quality that you know. But we've got a function that has to be respected as to range. So when we apply the inverse equations, we must respect the range of the inverse cosine function, which is, again, 0 to pi. So we can start this problem by restricting, that is, looking at x between 0 and pi over 2. And what we want to be able to do is apply the inverse cosine to this inequality, just like we do with algebraic regions. So remembering that this is a decreasing function, we know that the inequality will reverse when we actually apply the inverse cosine. So what we get is the inverse cosine of cosine x, the inverse cosine of y, and then lastly, the inverse cosine of 0. Of course, we know the inverse cosine of 0 is pi over 2, so we have that here. And now, of course, the inverse equations are valid because x lives between 0 and pi. So we just get the input. That is, when we apply the inverse equations, the input is the output. And of course, this term, the inverse cosine of y. And now I'll put a box around this because this is the important part. This gives us the upper bound for the dependent variable x, which is very useful to us. So now, is the other part just as simple? Well, not really, but let me show you how we can actually attack it. Before we do that and do these calculations, I want you to see some of your review from pre-cal or trigonometry. So what I've written here are some useful ideas that you would have studied when you took those courses. The first one is a really useful identity. The inverse cosine of the negative argument is pi minus the inverse cosine of x, of course, without the negative. The inverse cosine is not an odd function, so you don't get that luxury, but this is something that's you would have proven in your pre-calculus or your trigonometry class. So that's something we're going to use, so we need that. Now, the other part is that, of course, now the x is between negative pi over 2 and 0. So that would be a fourth quadrant angle. So what I'm doing here is I'm just taking alpha to be in that particular interval. So I just write the points on the unit circle, and I guess I'll just call this S1. You know, S1 is the one-dimensional unit sphere, which is the unit circle. So this is, how do we write it? X squared plus y squared equals 1. That's our friend. And we, of course, know the x coordinates are cosine and the y coordinates are sine, which I have here. So what we want to do is figure out an identity that will allow us to apply the inverse cosine. So what I've done here is I've simply created a transformation along the unit circle by pi radians. And that will take us, if you start here, to cosine of alpha plus pi and sine of alpha plus pi. But now, of course, this is just giving us a projection through the origin. So this is also equivalent to the additive inverse of cosine alpha and the additive inverse of sine alpha. So again, just using symmetry, we get so many nice results. So of course, these two expressions are equal. So I've written that here. Cosine of alpha is equal to the negative of cosine of alpha plus pi. Now, why do we even care about that identity? What we can do is now look at the calculation here, which is very simple. That is, we know x is between negative pi over 2 and 0. So if we add pi, we get pi minus pi over 2, which is pi over 2, and then x plus pi here, and then 0 plus pi, which is pi. So now x plus pi lives in the range of the inverse cosine. So this is actually very important because now if we apply the inverse cosine to cosine, the inverse rules are valid. That is, input equals output. And we have to respect that. That's something that is very difficult to do when you're used to the standard trig functions, which, you know, you don't really have to even think about it. You just don't want to divide by 0, but those are so much simpler, than the rigged, so to speak, inverse trig function. So now let's go back to the first page and finish the calculation. So just like we saw, we're now going to replace the cosine x here with the negative of cosine of x plus pi. So our new inequality looks just like this. Now we can apply the inverse cosine, but remember this is a decreasing function, so everything reverses. So we have inverse cosine of the negative of cosine of x plus pi. We have the inverse cosine of y, and of course our friend, the inverse cosine of 0, which is pi over 2. And then of course the inverse cosine of y, no change there. Now, at this point, we want to use the identity, we have the inverse cosine of the negative argument. So this is pi minus the inverse cosine of no negative. That is, that absorbs, we have cosine of x plus pi. So now this part is just the input equals the output. So we just get x plus pi. So that gives us pi minus x plus pi. The pi is absorbed and we're left with negative x. So now we have an inequality that's starting to look just like this one, but we don't need the negative. So of course we multiply by -1, reverse everything. So we have x is greater than or equal to the additive inverse of the inverse cosine of y, which is greater than or equal to negative pi over 2. Just like up here, we box the part that is important to us. So now we have a lower bound for the dependent variable. Here, we can couple that with the upper bound of the dependent variable. And therefore, we have the new description that is now y runs from 0 to 1 and x runs from negative inverse cosine of y to inverse cosine of y. So your intuition probably is validated by what we just did, but it's important to realize that when you work with the inverse trigonometric functions, you must really respect the range and domain, because otherwise you write down nonsense, and we don't want to do that. So of course, with these new descriptions, we could actually compute the integral with the first description, or we could compute the integral here with our new order, our second description, and we are done.